Let's apply what we've learned to ideal gases. Let us consider the Carnot cycle as shown on our PV diagram. Recall as we go from state 1 to 2, we have isothermal heat addition. As we go from state 2 to state 3, we have reversible adiabatic expansion. From 3 to 4, we have isothermal heat rejection, and from 4 to 1, we have adiabatic reversible compression. Our reversible work is given in terms of our pressure and specific volume for an ideal gas. That is, delta W is equal to P d nu. Or, using ideal gas law, this is RT per nu d nu. The change of internal energy, du, is equal to constant volume specific heat for an ideal gas, CV naught, times our change of temperature, dt. Thus, the heat added to our system, delta Q is equal to du plus delta W, or CV naught dt plus RT per nu d nu. Now let's apply our conservation of energy equation formulated for an ideal gas to each of the 4 processes. Let's consider the process going from state 1 to state 2, where we have an isothermal heat addition process. In an isothermal heat addition process, our temperature does not change. dT is equal to 0. Delta Q is equal to CV naught dt plus RT per nu d nu. Or our heat supplied going from state 1 to state 2 is simply equal to our gas constant times our high temperature, TH, times the natural log of nu2 per nu1. If we consider our adiabatic expansion process going from state 2 to state 3, Q, our heat supplied, is equal to 0. That is, 0 is equal to CV naught dt plus RT per nu d nu. Or 0 is equal to integral from our high temperature to low temperature bound, CV naught per T dt plus R times the natural log of nu3 per nu2. That is to say, the integral from TL to TH of CV naught per T dt is equal to R times the natural log of nu3 per nu2. Keep track of this equation. It's going to become important shortly. If we consider our isothermal heat rejection process going from state 3 to state 4, our heat is equal to negative R times TL times the natural log of nu4 per nu3. Or this could be expressed as R times TL times the natural log of nu3 per nu4. Lastly, if we consider adiabatic compression going from state 4 to state 1, once again Q is equal to 0, we'd have 0 is equal to CV naught dt plus RT per nu d nu. And evaluating this between our bounds, we have 0 is equal to integral from TL to TH of CV naught t dt plus R times the natural log of nu1 per nu4. Or we can say the integral from TL to TH of CV naught per t dt is equal to minus R times the natural log of nu1 per nu4. Now we note for our 2 adiabatic processes, we have the same integral, both the bounds and integrand. That is, we had the integral from TL to TH of CV naught per t dt. And this was equal to minus R times the natural log of nu1 per nu4, which was equal to R times the natural log of nu3 per nu2. Or we'd have the natural log of nu4 per nu1 is equal to natural log of nu3 per nu2. Or we could have the natural log of nu1 per nu4 is equal to natural log of nu2 per nu3. Whichever way we deem to express it, we're going to be interested in the quantity of our ratios of our specific heats of our 2 isothermal processes. That is, nu3 per nu4 is going to be equal to nu2 per nu1. If we recall the definition of our thermodynamic temperature scale, in particular our ratio of heat rejected to our heat input, QL per QH. This on a per mass basis, expressed for an ideal gas, is Q going from state 3 to 4 per Q going from state 1 to state 2. This is equal to R times TL times the natural log of nu3 per nu4 per R times TH times the natural log of nu2 per nu1. And we saw in the previous slide, nu3 per nu4 was equal to nu2 per nu1. Thus our R's and natural logs cancel out, and thus we are left with TL per TH. That is, QL per QH can be re-expressed as TL per TH. Thus, we have the same thermodynamic temperature scale for ideal gases as we already derived for the Carnot cycle.